This lecture will be going over the ordinary least squares solution. The reading for this lecture is Chapter 3, Linear Regression, in the book An Introduction to Statistical Learning with Applications in R. If you have not read this chapter, please pause, go read it, and come back. We will be going over two primary topics in this lecture today: maximum likelihood estimation in the linear regression context, and model evaluation approaches. First, let's start by talking about maximum likelihood estimation. In the lectures on linear models and bias variance trade-off, we talked about how the fundamental form of a linear regression model is that your output y, your response or dependent variable, is simply described by a linear set of inputs or predictor variables x that sum together, and each one is scalar multiplied by regression coefficients, in this case betas. And then there's some associated noise, epsilon, that cannot be accounted for by x. Now you'll recall from the linear models lecture that if you meet the assumptions of a standard ordinary least squares linear regression problem, then finding these regression coefficients is fairly trivial. They have a closed form solution. The intercept, beta naught, which reflects the mean of y after accounting for all the influences of x, is simply the mean of y plus the summed regression effects on the average x. So every term x that you have, every column in your x matrix, if you take the average x and multiply it by the regression coefficient, what's left over is the effect for the intercept. Now you need to know what these beta hats are for your x terms. Those are solved by this equation here, where for every x that you have, for every variable that you have to predict y, the regression effect is just the covariance of that term with y over the variance of x. Now, what I want to do today is show you how we get here, how we have this closed form solution, to give you a deeper understanding of the process by which we fit our models. If you recall, the assumptions of linear regression, standard ordinary least squares linear regression, are that the function f of x describes a linear relationship between x and y is normally distributed, there is no collinearity or correlation between features in x, and f of x is stationary. And some of these terms define or fall under the condition of being independent and identically distributed variables. Now, why do we have these assumptions? Well, with these assumptions, your error, or in this case, your residual sums of squares of your model, has this convex shape. So here I'm showing the residual sums of squares when your beta hat I, let's just say you have one term x, so your regression coefficient for x changes value. And so the optimal regression coefficient for this term is this point on this curve where you hit your lowest basically value, your basin here of this gradient of errors. Now we've talked about this as being your residuals. So if I fit a model and I calculate out the error between every observation of all n observations that I have squared, that defines the overall error of my model. The plot on the left is showing the sum of those for different values of your model, for different model fits. One of the critical assumptions of ordinary least squares regression is that these errors are normally distributed. We will assume that y is normally distributed such that these residuals are normally distributed. This assumption, if it's met, means that your errors will always have this convex form, which makes finding the minimum easy. In order to understand how this works, we have to get comfortable with a particular concept known as a likelihood function. The likelihood, or the likelihood function, is simply a probability function that describes the probability that your data or the data that you observe arises from a specific probability distribution with a specific set of parameters. So for example, the likelihood of x given a particular mean and a particular variance, in this case mean mu and variance sigma, if you assume a Gaussian distribution, follows this functional form. This is simply saying that if I think x comes from a normal distribution, if I know mu and I know sigma, I can determine the likelihood that x comes from that distribution. That follows this form. And this is important because the specifics of this equation that you see on the screen that describes a normal distribution allows for solving the derivative of your errors. And that's what gives us your best fit. So if we return to our residuals for a second, remember again, we're assuming that your residuals are normally distributed. If we assume they're Gaussian, then that means the likelihood of the data that you're seeing, given your model fits, can be described by this equation here on the left. So the likelihood of your data, your y, being produced by your inputs x and a model with regression coefficients beta naught, beta 1, beta 2, all the way up to beta p, and some internal variance sigma, can be described as the product of these Gaussian errors. So that probability distribution of the data you observed, and again, this is now the probability of y, given your inputs and those regression coefficients and your variance, is just this product across all of your observations as the difference between what you observe, yi, and these summed regression effects. So this term here is just showing that it's a product. Now, if y is normally distributed, then the residuals of the model f hat of x fit to y should also be normally distributed. This is a key assumption here. So now we can work with this likelihood function. We can say if we fit some specific set of regression coefficients, what is the likelihood of seeing the data that we have, y, given a model with these inputs? And with this assumption, that answer to what is the best beta hat comes out in the wash. It comes out as a simple closed form solution. Now, before I get into kind of details on this proof, I just want to do a refresher from algebra on logs. So remember that the log of an exponential with terms a minus b is the same thing as log of the exponential a minus the log of the exponential b, which just comes down to a minus b. Hold that in your head as we go through this proof. So what I'm showing here now on the left is just a repeat of what I showed you a couple slides ago. This is the likelihood of the residuals, which is the product of the probability of every yi that I observe given your input x, your regression coefficients, and a variance. Taking the product here is hard. It's hard to work with products if you're trying to come up with a solution for every beta hat. But we can convert these products into sums, which are much easier to work with, by simply taking the log of this likelihood function. So if we take the natural log of your likelihood function, it takes that product and turns it into a sum. So now I have the sum of the log probabilities of my data y, given x, my regression coefficients and variance, which, with a little bit of rewriting here, if you assume that that probability distribution is normal, comes down to this form here. So the log likelihood of a Gaussian distribution of errors comes down to negative n over 2 times the natural log of 2 pi minus n times the natural log of sigma, that model variance, minus 1 over 2 sigma squared times the sum of all observations 1 through n of the difference between yi, that observation, and the model that you use to predict yi from the regression coefficients that you fit squared. In other words, times the sum of all the squared residual errors. This is the form of the log likelihood of your data given your specific model fits. Now the goal here with model fitting is to maximize this likelihood. You want to find the set of regression coefficients, all your betas, that maximize the likelihood of observing the data that you have, the y's that you have, given those terms. So maximizing the likelihood of your data given your particular model, or in this case, the fitted regression coefficients, means finding the parameters that maximize your error cost function. That minimize your error cost function. So the relationship between your error, let's say your mean square error here, shown in red, and the log likelihood of y given your model has this relationship. So where your mean squared error is its lowest is the point at which the log likelihood of your data, or the likelihood of your data, is highest. This is why we're trying to find the bottom of that convex gradient of error, that red line we're showing here. So our task is to find those regression coefficients that are at that convex bottom, or the bottom of that convex distribution. So let's return to our mean squared error. Remember, our mean squared error is just the average of our residual sums of squares. So I can define the mean squared error as the expectation of all y's minus my regression equation. Here I'm just including a single x term just for simplicity. We can expand this out as being the expectation of y squared minus 2 times beta naught, the intercept term, times the mean of y, minus 2 times beta hat 1 times the expectation of x times y, or the mean of x times y together, plus the expectation, or the mean, of your fit model squared. So the expectation of beta naught plus beta 1 x squared. This is just simply an expansion of that first term in your mean squared error definition. We can expand this further now to this equation, where again we keep with the expectation of y squared, or the mean of y squared, minus 2 times beta naught times the mean of y, minus 2 times beta hat 1, or beta 1, times the covariance of xy, plus the expectation, or the mean of x, times the expectation of y, plus the squared intercept term again, beta hat naught, or beta naught, plus 2 times beta naught times beta 1 times the mean of x, plus beta 1 squared times the mean of your squared x. All we're doing is expanding out this equation. And I'm going to expand it out further so we can get to something that we can now individually solve for beta naught and beta 1. So this expanded version cleans up those terms, and this is the final version of the mean squared error that we're going to work with. So your mean squared error is defined as the expectation of y squared minus 2 times beta naught times the expectation of y, minus 2 times beta 1 times the covariance of x and y together, minus 2 times beta 1 times the expectation of x and the expectation of y, plus beta naught squared, plus 2 times beta naught times beta 1 times the mean or expectation of x, plus beta 1 squared times the variance of x, plus beta 1 squared times the expectation of x, and that is squared. This is a pretty long expansion of the mean squared error term, but you'll see why it's useful to expand it out to here, because this is the point at which we're going to calculate out our derivatives to find the point on that convex curve where the mean squared error is the lowest. Now, just some friendly reminders here on partial derivatives. The derivative of x squared plus y with respect to x comes out to being 2x. When I say the expectation of x, I mean the mean of x. The expectation of x squared is the variance of x plus the expectation of x squared. The expectation of x times y is the same thing as the covariance of x and y plus the expectation of x times the expectation of y. These are just some useful reminders from introductory to statistics and calculus that are going to be helpful for solving the maximum likelihood estimation problem. Now remember, we want to maximize the likelihood of your data given a particular set of models by finding the minimum of your mean squared error. If we take that expanded version of the model that I had shown you before, that mean squared error that I showed you before, what we're going to do is we're going to remove, or we're going to take the derivative for individual betas. In this case, we just have beta naught and beta 1, and find where that derivative is 0. That will be the lowest point on this convex curve. Now, in the case of our intercept term, if we take the derivative of that mean squared error function, what we're left with is negative 2 times the expectation of y plus 2 times beta naught plus 2 times beta 1 times the expectation of x. We can simply rewrite that down to what we've seen before, because the 2's cancel each other out. So that brings us down to the expectation of y minus the expectation of x times beta 1. So it's just the mean of y minus your beta 1 times x. And this actually works if you have multiple x's, but we're just showing the case where you just have a single x variable right now for simplicity. Now you notice I can't answer what my beta naught is until I know what my beta 1 is. So now let's solve for this other regression coefficient, beta 1. Again, we're going to start with this mean squared error term, the expanded out mean squared error. We're going to take the derivative of that with respect to beta 1. If we take those derivatives, we get negative 2 times the covariance of xy minus 2 times the expectation of x and the expectation of y, plus 2 times beta naught times the expectation of x, plus 2 times beta 1 times the variance of x, plus 2 times beta 1 expectation of x squared. Now we can rewrite this again because, again, a lot of those 2's cancel out. If we solve for 0 and try to get beta 1 back out, what we get is the covariance of xy over the variance of x. So if you set this to 0 and solve for beta 1, what you return is the equation that we saw before. The covariance of xy over the variance of x. Now, showing this step from taking the partial derivative of beta 1, setting it to 0, and solving for beta 1 itself is left as a homework problem. So that will be up to you later. But you can see how, if you trust that the math works out, it's very simple to know what the minimum of your mean squared error function is, because all you're doing is solving for the point at which that derivative is 0. Now, because we have beta 1, we can plug it into our beta naught equation, which just kind of expands out what the beta naught is in its closed form solution. This is the beauty of the ordinary least squares regression problem. You don't have to do any complex gradient fits or iterative fitting algorithms. All you have to do is verify that your data meets the assumptions of ordinary least squares regression. And if so, the answer to all of your regression parameters in your whole model is algebra. That's it. And this is the optimal solution. So taking a step back, we can start to understand a little bit how the original assumptions make sense in the context of the maximum likelihood solution for the ordinary least squares problem. So with MLE, in this context, it provides a well-defined probability distribution and convex error gradient. That convexity is important. Having that simple shape to your error gradient allows for finding your optimal minimum. So it allows for solving each regression coefficient separately. And there's only really one function to solve for. In fact, if you look at the matrix algebra way of framing the ordinary least squares solution, it's one line of linear algebra. And we will go over that in another lecture. So the assumptions link to each one of these advantages for the ordinary least squares solution. With y being normally distributed, the residuals are also going to be normally distributed, which gives you that convex error gradient. The linearity assumption allows for solving each regression coefficient separately. The fact that they're not correlated across X also allows for this. And the stationarity assumption allows for the ability to just solve the problem in a single function. You're not solving mixture models, you're solving a single problem. So this is why we hold on to these assumptions so tightly in the linear regression context. Now, there are other ways of fitting linear models. There's a whole class of fitting linear models that don't abide by these assumptions. And there are many more advanced courses you could take to understand these more complex regression problems. I'm just focusing on the ordinary least squares solution because it's the most intuitive way of understanding optimal solutions in these regression contexts. The ordinary least squares solution is the optimal solution if all those assumptions are met. But optimal is just saying the best that you can do. Once you fit your optimal model, you want to know how good is it doing? How well is it at explaining the reducible error? And how much irreducible error is left over? So this gets into the concept of model evaluation. And we're going to go over formal statistical tools for evaluating how well your model does at explaining your data. Let's return to that residual sum squares gradient for a second. Remember, we just spent the entire first part of this lecture focusing on finding the minimum of this convex function. But the height of this convex function, where this minimum point is the indicator of its overall performance. And in an ideal world, your model will account for all the variance in your data. If you have a perfect model fit, the residual sums of squares at that point where you have your lowest point in that error basin will be 0. So that line will intersect 0. However, that's not often the case. And if you have extra variance in your model, or you have irreducible error, you have other sources of, let's say, violations of the assumptions of ordinary least squares, whatever, that residual error is going to be non-zero. So you want to find a way of quantifying that distance from the minimum of your residual sums of squares to 0. One metric that we've gone over before in previous lectures is the residual squared error term, RSE. This is the variance of your model itself. So it is the residual sums of squares divided by a degrees of freedom of n minus 2, and you take the square root. Now remember, your residual sums of squares is just the sum of every observation yi minus the model prediction of that yi. RSE is nice because it's bounded at 0. 0 is the goal you always want to try to hit with RSE. You never really hit it, but at least you know you have this lower bound. It is the easiest to calculate. It's just the sum of your predictions minus your observed, or your observed minus your predictions squared with the degrees of freedom term. The lower the RSE, the greater the model fit. And it is the closest evaluation of y hat itself. So it is the most cleanly linked error estimate to y hat itself, your prediction itself. Another measure that has, I think, more intuitive value is the coefficient of determination, or R squared. R squared compares the total sums of squares to the residual sums of squares. So it's typically defined as the difference between the total sums of squares minus residual sums of squares over the total sums of squares itself, which can be rewritten as 1 minus the ratio of the residual sums of squares over the total sums of squares. It's a direct measure of variance in y that can be explained by your model f hat. It is a percentage term. So that increasing R squared means greater model fit. The higher the R squared is, the closer to 1 it is, the more variance that you're explaining with your model. And it's in these interpretively meaningful units. The value ranges from 0 to 1, or 0% to 100%. Your best fit model will explain 100% of the variance. And to see how that works, imagine you have a perfect model where RSS, the residual sum of the squares, equals 0. In that case, in that middle term of 1 minus residual sums of squares over total sums of squares, that second term becomes 0, and you're left with 1. The higher that ratio of residual to total sums of squares, the farther away from 1 you get. Which means that the less variance that your y hat explains relative to the mean of y itself, the lower your R squared is going to be. Finally, you can take the f-test itself, which we've talked about in the context of ANOVA, and use it as a direct measure of model fit as well. And again, this is just a variant of what we just saw before. So now it's the difference between the total sums of squares minus the residual sums of squares over the residual sums of squares itself with relative degrees of freedom terms. Like the RSE, or the residual squared error, this is bounded at 0. Like the coefficient of determination, higher f values means greater model fit because you're getting a greater separation of the total sums of squares from the residual sums of squares. And it's a ratio of variances, again. Variance explained by f hat versus the overall variance of y. Now, the RSE, R squared, and f model evaluations all basically are reflections of a common theme for evaluating your model. And this is central to most model evaluation techniques that we'll look at in this class. These model evaluation measures look at how well the prediction, y hat, explains variance in y compared to just the mean of y itself. So I have a y, a distribution of y terms, and remember, they're normal. So I have a mean y hat. Without any other information, the best prediction I can make of any observation of y is simply the mean. If I don't know anything else about this data, the most likely observation I'm going to see is the mean. That's my best predictor. So what these model evaluation terms are doing is comparing how well your model's doing with additional information, in this case your x terms, compared to just explaining y with the mean itself. And you can think of the total sums of squares as just being the variance of y. That is the fundamental comparison of all model evaluation techniques that we're going to look at. Is how well does your model in that fit and your best fit separate itself from just the mean of y itself. If you can't do better than the mean of y, your model is no good. We'll keep coming back to this throughout the class. What I would like for you to take away from this lecture is that ordinary least squares regression provides a simple, closed-form solution to the model fitting problem, so long as the data meet the assumptions. If you have a data set of inputs and outputs that meet the assumptions of ordinary least squares regression, this closed-form solution is the best you will do. You can get it quickly, it's simple, and it's optimal. So this is the beauty of ordinary least squares regression. It's really quick and simple to calculate and will give you the best solution possible without having to do things like gradient descent or other more complex forms of model fitting.